This presentation is by Ryan Kophs, Jeff Lassen, Luke Connors, and Eric Bueno. The topics we will be discussing are context-free grammar, concrete syntax, expressions and strings from concrete syntax, abstract syntax and parse trees of strings, ambiguity of strings and expressions, and lastly, left and right associativity. First, we're going to talk about context-free grammar. The definition of context-free grammar is a set of formation rules for the strings in a formal programming language. These rules describe how strings and sentences can be formed according to a language's alphabet, and these rules also describe the syntax of a language. It's important to note that the syntax of a language only describes how strings can be formed and not the meaning of strings. Below is an example of what the syntax rules for a context-free grammar might look like. First, we will talk about concrete syntax in a context-free grammar. Concrete syntax of a language conveys how you can form expressions and statements using a program's alphabet, and it does this with production rules. Below you see 3 different production rules. They're entitled integers, numbers, and digits. Production rules contain terminals and non-terminals that you can use to expand your language to create longer strings and sentences. Alright, so now we need to describe a little more what terminals and non-terminals are in our production rules. Terminals are all of our symbols that make up the alphabet of our grammar that we are defining. They are symbols, and they are the only things that will appear in our strings. Non-terminals never appear in a sentence or a string made by your context-free grammar. As shown in the previous slide, these are 3 production rules. The italic I, N, and D all represent non-terminals. And as you can see, they all produce either another non-terminal or terminals, which are symbols. As you can see from looking at our production rules, if you start with an I, you can create a non-terminal N or a negative N, which then creates either a digit or a digit followed by another N, and no matter what, your last thing that you are creating from your production rule ends up being some sort of terminal and some sort of symbol, and that ends your string eventually. And so this is the way that we use non-terminals and terminals in our production rules along with our alphabet to create strings in our context-free grammar. Alright, on this slide you see the context-free grammar that we are going to be using for the next few slides for a couple of our examples. There's 2 production rules with this context-free grammar, and the alphabet only consists of 3 symbols. An A, a lowercase b, and the and symbol. And below you can see some resulting possible strings using our production rules that we can make A and A, B and B, A and A, and B and B, and essentially you can make almost any string resulting in A's and B's, but they have to be separated by the and symbol.
We will now take a look at abstract syntax. Abstract syntax of a programming language is the representation of programs used by language implementations. This allows us to represent our context-free grammars using parse trees. A parse tree is a model that shows us how to form expressions using a particular grammar. We can also check if an expression given to us is in that grammar. Parse trees are useful in showing different concepts such as ambiguity and associativity, which we'll do later. For our example, we'll have this expression A and B and A, and using our abstract syntax and parse trees, we'll show that it is in the grammar. First, we will start with A. Using the definition, we see that A expands to A and A. We will then continue to expand the leftmost A into A and A again, but we still have the last A and A. Then we will, using our grammar, we expand each A into a V, as we can clearly see that the A's can be represented by V's. We'll then take this one step further and substitute A's and B's in places of the V's. At the end, we can see that we clearly have A and B and A using our abstract syntax and parse trees, which shows that this expression is in our context-free grammar.
Ambiguity exists when a grammar can parse a string in more than one way. Specifically, ambiguity exists when a grammar is able to create different abstract syntaxes from a single string. Remember that abstract syntaxes are represented in parse trees and that your concrete syntax is the single string that is being parsed. For example, in the C language, x asterisk y ending with semicolon can be parsed and later interpreted to be either an identifier y pointing to an allocation of memory of type x or as an identifier y multiplied by an identifier x. Both of these parsed results from the same string clearly have different meanings. In the previous example, the A and B and A string can be parsed as a tree where the A and B is to be interpreted before the ending A, as in the previous example, or parsed as a tree where the B and A is to be interpreted before the beginning A and B. Looking at this example again, we have already developed the following parse tree where the first A and B are to be interpreted first on the left side of the page. Now we will show the latter where the B and A is to be interpreted first. Using the top definition of the grammar, we're able to expand the A into an A and A. Again, we're using the same definition and expanding each capitalized A into a capitalized V using the first definition once again, and using the last definition, expanding these V's into lowercase a's and b's in order to represent the A and B and A string in a different parse tree. As seen, both parse trees are different, although they are derived from the same single string A and B and A, and therefore the grammar used in this example is ambiguous.
Now that we've seen a general example of ambiguity when it comes to grammars, we will take a look at another example of ambiguity, and then we will see how to fix this, and how by fixing it we get associativity. In this first example, the order of operations is unclear. If we assume 100 should be divided by 10, and then divided by 5, we will arrive with 2 as the answer. On the other hand, it is also possible that 10 should be divided by 5 first, and then 100 divided by 2 in order to get 50 as the answer. As you can see, this first grammar is ambiguous and will lead to confusion. However, an easy way to solve this in this grammar is to force either the divisor or the dividend to be a terminal. If you do this, and then begin to make a parse tree as before, you will notice that the tree will grow deeper in only one consistent direction. This is what we call associativity. In the non-ambiguous grammar on the left, and its corresponding picture on the left, you will notice that the tree grows deeper towards the left. This grammar is left associative. The same goes for the right associative grammar on the right. You can check in the left associative case to be sure by noticing that in order to divide anything by 5, you must first evaluate what 100 divided by 10 is. There are more complicated examples of associativity. One example would be the grammar necessary to implement all of the order of operation rules, but we will not go into that here. Thank you for watching, and we hope that you've learned more about grammars, syntaxes, ambiguity, and associativity through this presentation.